Hi everyone, this is Jake Fry, and today I'm going to discuss units of measurement. So, you might be wondering, why do we need units of measurement? And in fact, in science, without units, we could not understand the meaning of measurements at all, or how they compare with other quantities. And so it's very common for people to omit saying the units when they're talking with friends, but if you're trying to write, scientific paper, and have someone you don't know read it, they would have no idea what's happening without the units. So for example, if you see a car traveling and you say, oh, it's traveling at a speed of 60, we would be unable to know how fast this is without the unit. It could either be, say, 60 miles per hour, or 60 feet per minute, or any other unit of speed you might imagine. So what's the standard set of units? So in science, it's the International System of Units, or the SI system. And you might notice that it looks very similar to the metric system, which it's what it's based on. So, what are the most common units? So they're split into two different types. One are the SI base units, and so these are defined as the main units of the system. And anything that uses multiple of those units in some combination, like multiplying or squaring them, those are derived units because you have to use the base units and some arithmetic in order to derive new units. Okay, so what are the SI base units? So for time, it's the second and not like the hour or the minute. For length, it's the meter. For mass, it's the kilogram, and so lots of people in chemistry use gram instead, so just be careful that it's actually the kilogram. And then for electric current, it's the ampere. For temperature, it's Kelvin and not Celsius, so it takes into account absolute zero as its starting point. And then for the amount of substance, that's the mole. And for luminous intensity, that's the candela. Cool. All right, so now what are derived units? So we will see in later videos that there are many units that are derived from those base SI units. So, for example, the unit of energy is the joule. You might wonder, why do we need derived units? Well, it's because it's very difficult both to say and write the units fully in the SI base units. So for example, if I have an engine and it generates 100 joules of power, that's pretty easy to say and write. But if I were to use the SI base units for the same amount of power, I would have to say, okay, this engine has 100 kilograms meter squared per second squared of power. And so that's much more difficult, as you can probably tell. All right. And so one thing to keep in mind is kind of like a rule in order to make solving problems more easily, is basically use SI units throughout each physics or even engineering problem. And in this way, you'll never make mistakes in the calculation by having to do extra unit conversions, because then you would have to be really careful with what each number's unit was. It's usually good to pay attention to the unit on each number anyway, but by minimizing the number of calculations, you'll maximize your chance of success. So, for example, if you are given some kind of physics problem and you're given something that's not in the SI system, so say you're, excuse me, you're given, say, length in terms of feet, and you know that you're trying to get something like, the velocity in the end of the problem, and you're expected to have it in meters per second, which would be the SI system. Always convert from feet into meters first, and then you won't make any mistakes at the end. Cool. All right, so now what are some other conventions for units other than the SI system? So in many cases, scientists will make special systems of units for the experiment in question that are much more convenient. So for example, I work in the field of ultra-cold atomic physics, And so we deal with things like several hundred thousands of trapped atoms. And so that creates a cloud that's much, much less than the density of air. So the mass unit of, say, a kilogram would be extremely inconvenient. And also, when you're talking about atoms, length scales of meters would be humongous. So instead, we create non-SI units, such as the atomic mass unit for mass, or the Bohr radius for length. And sometimes you'll be reading papers, especially ones that are very mathematical or, say, theoretical physics papers, where they'll redefine constants of nature or even units to have a magnitude equal to 1, which makes their all of their calculations easier because you can always multiply by 1. And so you'll see things like, the speed of light, for example, having a speed equal to 1. And so, that's not true in real life or in SI system, but it would make many calculations easier. So just be careful. Okay, so now on to unit conversion. So remember, you can always multiply any number by 1 and retain the original value of that number. And it doesn't matter how strange the number 1 looks. For example, 10 to the negative 6 meters divided by 1 micrometer equals 1. So, since it's 1, we can multiply it by anything. For example, you can convert 3.5 micrometers into 3.5 times 10 to the negative 6 meters because you multiply the 3.5 micrometers by 1. But 1 is 10 to the negative 6 meters over 1 micrometer. And then you can treat the units, micrometers, as like a, I guess a variable. It's not really a variable, but you can treat it similar. So you can cross out what's in the numerator, that micrometers, with what's in the denominator, the unit micrometers. And so you end up with just 3.5 times 10 to the minus 6 meters divided by 1, which gives us what the right-hand side was. Cool. And so basically, I guess before moving on, you just have to choose what type of 1 you want to multiply by in order to get rid of the unit that you don't want and turn it into the unit that you do want. Okay, now on to significant digits. And so why would we want to use them, what they are, and how to keep track of them. So in measurements, we do not want to claim more accuracy than our measurement device can achieve. And so this is essentially a way to keep track of the resolution in any experiment. And so in any calculation, the way that we do this is we use the least accurate measurement device to determine the overall number of significant digits. And so this might seem weird in the digital age. We can have almost infinite decimal points on each number. But if you were to try to measure something, say with like a ruler, and you're trying to see the length, that you'll have little tick marks that separate each of the locations on the ruler, and so eventually you won't be able to tell by just eye where the measurement of length is between one tick mark and another. And so using significant digits allows you to keep each measurement and then each calculation in check so that you always have a justifiable resolution in the end for your results in your experiment. Okay, so usually the best thing to do with any value that was measured is to convert it into significant digits. And this is because you won't get confused by some of the rules, such as like the leading zeros when they're, before the decimal point, or sorry, leading zeros before the numbers are non-significant, but zeros after the decimal point are. So that can be very confusing to try to keep track of all those rules. I'll go through all the list of rules in a second, but I would recommend just converting into scientific notation, because then you always know that what's being multiplied by 10 to whatever order. So that in this case 6.20, you would have 3 significant digits because there's 3 numbers there. So it makes it far more easy in order to keep track of significant digits. Okay, so some of the rules. So first, all non-zero numbers are significant, and then all zeros between non-zero numbers are significant. So for example, if you have the number 101, that has a significance of 3 digits. Leading zeros are not significant. So that was like in our previous shown example where we have a bunch of zeros before the 620. So those are non-significant. But then trailing zeros are significant. And so this is either after the decimal point. If you have a bunch of zeros, that says that those are significant. And then if it's before the decimal point and then you end the number with a decimal point, so if you have like 1, 0, 0 decimal point, then that's like making a punctuation, like, okay, all of those zeros are significant. So it'd be 1, 0, 0 decimal point, so 3 significant digits. All right, and then exact numbers or rational numbers have infinite significant figures. And so these are the like defined numbers that you might remember from geometry or trigonometry, such as the number pi. And so the reason for having this pi, so which helps you find the circumference of a circle, for example, having infinite significant figures is so that there's no chance that no matter how well resolved your experiment is, there's no chance that having pi be defined as something less than an infinite significant figures will corrupt your resolution. So like if you were to choose, instead of using pi with infinite accuracy, you chose 3.14. And so you might say, oh, that's only 3 significant digits. And so if I'm multiplying that by a measurement that has 4 significant digits, then I end up with 3 significant digits. So definitely don't do that. You would still end up with the 4 significant digits, because even though you only use 3 digits in pi, it is defined to have infinite significance. So just be careful. All right, and so that's all with the rules for significant digits, and that will help you if you have, a difficult professor or lab TA who requires you to always have significant digits. And so usually the best thing to do is to always round, and just make sure, since sometimes rounding rules can be weird. So I always like, if I have something that ends in a 5, I round up. But in some places you need a 6 to round up, so be careful. And some people will, so rounding is a lot less standard than the rules for significant digits. So I would recommend, if your teacher or professor or TA is requiring you to write out all of your calculations with the correct number of significant digits, make sure you know what the convention for rounding they use is. Cool. All right, so I'll see you next time.